Hi, and welcome to another review episode. This time we're going to cover nuclear chemistry and endo and exothermic reactions. One of the first things you need to know about nuclear chemistry are the three particles that are involved in nuclear decay. They are alpha, beta, and gamma. Alpha rays are the least penetrating, and gamma rays are the most penetrating. If you recall, gamma rays are also found in our electromagnetic spectrum, and they have the highest frequency and the shortest wavelength. So that kind of explains why they can be so damaging. So let's start with the charge of the particles. Alpha particles are actually a helium atom, so they would have a +2 charge. Beta particles are electrons, so they have a negative charge. And gamma particles are kind of unique. They have no charge at all. It's basically just a whole big blast of energy. Okay, so what is it made of? We just said this. A alpha particle is actually a helium atom. So there's your helium atom with its 2 protons and its mass of 4. Beta is an electron that gets released. Remember, electrons have a -1 charge and they have virtually no mass, so we assign them a 0. And gamma rays basically are just a whole bunch of energy like we said, so we're just going to put energy in this column. Okay, so remember when we said how you can, how penetrative they are? Alpha is the least, beta is the second most, and gamma is the greatest. With an alpha particle, you can actually shield yourself with some paper. They're emitted like out of smoke detectors and things, and they can't get very far from that. So you're pretty safe from alpha particles. Beta particles can be stopped by skin. For example, they can get in your first layer, but not in multiple layers of skin. And then gamma rays, we said how deadly and penetrative they were. It's going to take lead or several feet of concrete to block yourself from gamma rays. It's one of the reasons that an X-ray tech actually leaves the room when she takes your X-ray. Okay, so the symbol for alpha, there are 2 symbols you need to remember. This is the actual alpha symbol, but remember it also can be listed like this. Beta just looks like a fancy little bee. And remember, it is that electron. And then gamma rays looks like an upside down Cancer symbol, or like a fancy Y. And that's the only symbol you need to remember for gamma. Okay, its mass. 4. No mass. And then none. Gamma rays really aren't anything but a bunch of energy. Okay, so remember the 0 for the mass for the electron comes from here, and the alpha particle comes from here. Then the strength, as we said before, it increases. So the strongest of these would be gamma, the weakest would be alpha. Okay, so what happens to unstable elements or isotopes? Well, they decay. It's a natural process. Man can't speed it up, can't slow it down. So some of the uses that we have found for ourselves are carbon dating, nuclear medicine such as CT scans, X-rays, MRIs, different radiology tests, and then of course nuclear reactions. Another skill that you guys might have to do is fill in a nuclear equation. So these actually look complicated, but they're pretty simple. So if you were given an element on this side, so this is thorium, and see how it's decaying to radium, all you really need to do is subtract. So 230 minus 226 is 4. Okay? 90 minus 88 is 2. So, do you remember which particle had a 4 and a 2 with it? You're right, it's an alpha particle. So, we need a little helium molecule here, and we know that that is definitely alpha decay. What do you notice about this right here? See how there's also a gamma symbol? One thing that I failed to mention earlier is that gamma rays can be emitted with the other kinds of decay also. So, thorium decays into radium and an alpha particle with a gamma particle. That's how we would read that formula. Okay, with the second example, we have our alpha particle here, and we have radon here, but we don't know what element belongs here. Well, if it is on the right side of the equation like this, all you have to do is add them. So 222 plus 4 is 226. Okay, same thing here. 2 plus 86 is 88. Right now there's one thing missing. We do know this is alpha decay, but we don't know what our original element is. But actually you do. All you have to do is look up what element has the atomic number of 88. So if you would look at your periodic table, atomic number 88 is actually radium. Of course, you could have taken a shortcut and looking right here, but we didn't need to. We used our periodic table for that. Okay, so the last one we're going to do, here's the element on the left that's decaying. So remember, you subtract. And initially it looks like you're doing something wrong. 66 minus 66 is 0. 29 minus 30, think about to your integers, that would be negative 1. So what particle do we know that has no mass and a charge of negative 1? That's your electron. So what kind of decay would that be? You're right, beta. Very good. Just remember when you're doing these, everything on the left side has to equal everything on the right side. That's what balancing equations is all about. Okay, so let's take a look at another skill under the nuclear chemistry section, which is half-life. Half-life is simply how long it takes for half of a radioactive sample to decay. Some things it's seconds and some things it's thousands of years. So let's look at this example. You have a 30-gram sample of radium-226. It has a half-life of 1,620 years. How many years will it take until 7.5 grams of radium-226 remain? Well, the first thing I want y'all to remember is if it's given to you like this, that means it is an isotope. Right now, this number 226 is irrelevant, so don't worry about that. The numbers we are interested in are the 30, the 7.5, and the 1,620. So, how many grams of the isotope did you start with? It's 30 grams. How long does it take for half of it to go away? 1,620 years. So what I do is just dividing it in half until I get to the appropriate number. So we want to know how long it takes to get to 7.5, beginning with 30. Well, if you divide 30 by 2, you get 15. So that means one half-life has gone by. If you divide 15 in half again, you get 7.5. So that's the number that we wanted to get to. How many times did we have to divide to get there? 2. 2 half-lives would be 2 times 1620, which would be 3,240 years. So, in 3,240 years, you would have 7.5 grams of radium-226 left if you started with 30 grams. Another way they might show you a half-life equation is through a graph. So, this graph is showing you cesium-137. So, if you begin with this is where you begin. So, we're beginning with 100 grams of it, and it is decreasing by half as the years go by. So if you have to figure out what the actual half-life is, all you need to do is figure out where you started and what's half of that. Half of 100 is 50, and that took 30 years. So the half-life of cesium-137 is 30 years. All right, so an add-on question to that, if 3 half-lives have gone by, how many grams of cesium-137 is still undecayed? Well, all you have to do is count down 3 times. The only thing, you got to be careful, you don't count your initial amount with your half-life. So I would go 1, 2, 3. So this blue circled one here is my third half-life. Okay, it's not asking you how many years has gone by, it's asking you how much would you have left. So you look over to the left here, and I'm going to estimate that to be about 13 grams. Okay, the last skill that you need to know about nuclear reactions are the 2 types. They are fission and fusion. Although they sound alike, they are very different from one another. Let's start with fusion because I think everyone knows what the word fuse means. Fusion is when 2 smaller atoms join together to make a larger one. Okay, the perfect example of this is our sun. Gives you a tremendous amount of power. So your two hydrogen atoms are joining to make a helium atom, which is an example of fusion. And how I told my students to remember that is the word sun is actually in the word fusion. Okay, fission is the opposite of fusion. That's when you have a large, unstable atom that actually splits into two smaller atoms. Okay, so this one is joining, this one is splitting. An example of fission takes place in nuclear power plants or even some of our atomic bombs. Again, a tremendous amount of energy is associated with both of these. Okay, the difference between nuclear reactions and chemical reactions. With a nuclear reaction, your nucleus is actually going to change. The amount of protons and neutrons are going to change. So this is why these are considered nuclear, because the nucleus changes. Whereas a chemical reaction, your products here are going to be just a rearrangement of your reactants. Okay, so speaking of chemical reactions, our last topic today is exothermic and endothermic reactions. Just remember, exo means exit, endo means enter. So in an endothermic reaction, heat is going to enter the reaction. Okay, exothermic, heat exits. So if heat is going to exit, like it's showing in this picture here, it is actually going to feel hot. So what's going to happen to the temperature? It should rise. Okay? An endothermic reaction, if heat is entering, that means it's going to feel cold and your temperature should decrease. So some examples of these, if you guys have ever used a cold pack, like to put on a bruise or a sore area, when you punch that cold pack, you are mixing two chemicals together that form an endothermic reaction, so it feels cold and it brings the temperature down. For an exothermic reaction, if you guys have ever mixed two chemicals together and it got warm, like those heat packs, my dad takes them hunting, for example, so when he breaks the heat pack, it gets really, really warm, and like you can put it in your shoes or in your pockets to keep your hands warm. Okay, so that's the difference between those. Hope this was useful to you guys. Pause it, relook at it as much as you need to, and good luck with your exams.